as explained before, a closed cycle with external combustion is taken as reference for the gas turbine cycles, and this kind of cycle is called a Joule cycle. So here I have numbered the different key points we have in this cycle. We have A, the letter for the state we have at the inlet of the compressor, so cold temperature, low pressure, and then B is the outlet of the compressor, inlet of the hot heat exchanger. C is outlet of the hot heat exchanger, inlet of turbine. D is outlet of the turbine and inlet of the cold heat exchanger, and then we have again point A, and the cycle is closed. So we can first observe a few different things. First thing is that we have two extreme temperatures. A is the coldest temperature of the cycle, and TC, the inlet of the turbine, is the highest temperature we have in this whole Joule cycle. Then another thing that we can observe is that we have two key pressure levels, because we have two transformations only with pressure variations. That's the compression and the expansion in the turbine. So if we consider that there are no pressure losses in the heat exchanger, and that's usually the basic assumption, we can consider that B and C are both at the high pressure of the cycle, and D and A are both at the low pressure of the cycle. So we will first consider what we call an ideal Joule cycle. Ideal is related especially to the fact that we will not consider any irreversibilities during compression and expansion. So from a thermodynamic point of view, we will consider the compression to be reversible as well as the expansion. So let's try to plot what is happening for the working fluid in this ideal Joule cycle in a TS diagram. T like temperature and little s like specific entropy. So we can first start by plotting the four key things we have observed. First, the temperature of point A and point C, that are the extreme temperatures. So this is the coldest temperature, and this is the hottest temperature we have in the cycle. So because it's the y-axis, these isotherms are horizontal, of course. And also we can plot the shape of the low pressure isobaric line and high pressure isobaric lines, and that's what I have plotted here. This is the low pressure, and this is the high pressure of the cycle. So the general shape is going up in this diagram, and we can also note from the beginning that these curves are diverging when the specific entropy is increasing. So the distance between this isobaric line, or the temperature difference between these isobaric lines, is increasing when it's going to higher specific entropies. So where do we start? I would suggest to start with point A. Point A corresponds to the lowest temperature, so TA, and also low pressure, so the intersection between this low pressure isobaric line and the TA isothermal line corresponds to point A. Then we have a compression of the fluid from A to B. The compressors can, in gas turbine cycles, always be considered as being adiabatics. So we can completely neglect heat transfer that may occur with this with the ambient air around, because it is really neglectable compared to the technical work that is exchanged. So in that case, if we can say there's no heat exchange, there's no entropy exchange also. And in our case, we consider an ideal Joule cycle, so there is this compression is also reversible. Reversible means there's no entropy creation. So if there's no entropy exchange, no entropy creation, the entropy remains constant between A and B. So here, the x-axis is the specific entropy, so we can plot here the line corresponding to the specific entropy of point A, and the intersection with the high pressure, so at a higher temperature, here corresponds to point B, the outlet of the compressor. And so that's the transformation we had in this compressor. Then we have a heat exchange with the hot source of the fluid in the heat exchanger. So the heat exchanger can be considered as isobaric, and as the working fluid will receive heat from the other side of the heat exchanger, it will receive entropy. So the entropy and also the temperature of the fluid will increase across this heat exchanger until the highest temperature of the cycle, that is the temperature of point C. So at constant pressure corresponding to high pressure, here the temperature is increased until the temperature of point C here. So that's the highest temperature of the cycle. Then the gas is entering the turbine, and for the turbine we can do the same approximations we have already done before for the compressor. First is that the expansion can be considered as adiabatic. So the heat transfer is completely negligible once again, so there's no entropy exchange. In the ideal Joule cycle, we also consider the expansion to be reversible, so without entropy creation. If there's no exchange and no creation of entropy, once again the entropy remains constant, so we can plot the iso line that is vertical here, corresponding to the specific entropy of point C. And at the intersection between this specific entropy and the low pressure, this will correspond to the outlet of the turbine, point D. And finally, from point D at low pressure and considering constant pressure, then the working fluid will give heat to the cold source, and so it will give entropy to the cold source too, and the temperature of the fluid will decrease until being again at the state we had at the inlet of the compressor in A. So we can just follow here the low pressure isobaric curve until point A, and that's how we can plot this ideal Joule cycle in a TS